morning, guys, or afternoon, or whatever it is. I don't know, but I would like to welcome you to the last lesson of Chem 101. I know. Is it too good to be true? No, it is actually not too good to be true. It's totally the last one. But that means that we're gonna have like a vocab quiz and some reviewing and a practice exam, and then there's going to be another exam before we're done. So hold on tight, guys, because we are not done yet. Okay, so here's where we're going to like end things with is how, dude, look at those things. Look at these things. Like, what are, see the ones down there, the green ones? Like what is that even about? Like, okay, where do electrons even go in these things? It's kind of crazy, right? So we talked about before about these are all our orbitals, right? Our S, P, D, F, and there's also a G, but so beyond anything we as chemists are going to care about. So we talked about their numbers in the equation and how those quantum numbers basically are like a way of bookkeeping, so we know exactly where each electron is based on energy level. Energy levels tell us which orbital it is, and then which orientation that orbital is, right? The S, P, D, F orbitals and all that. Then there's the up spin and the down spin, so 2 electrons go into each orbital, if you remember that. So now what we're going to do is go from here to like how do the electrons start populating these things, right? So how do electrons start actually like for real filling in? So going back to the Schrodinger wave equation, we have quantum numbers, right? The energy level is N, L is the orbital, M sub L that's the orientation of that orbital, and then the M sub S is the spin, the up and the down. So there's only a plus 1/2 and a minus 1/2 for that, and that's like pretty much it, like for the M sub S. But I want us to remember that the set of these numbers, like N, L, M sub L, M sub S, basically describes where the electron is. It describes exactly which orbital and which electron is in it and what direction they're spinning, right? Which, when this last one, what direction they're spinning, that starts to become important because, it actually makes things magnetic. It does. And like the way that the electrons populate or fill in these orbitals is based on like lowest energy first. So the lowest energy fills, then up and up and up. And also with this, we have an explanation as to why that Bohr planetary model, why it kind of starts to fall apart with anything other than hydrogen. But like Schrodinger, this guy, figured it out, explained it away, predicted it with math, proved it with science. It's amazing. And so what we're going to learn about today is the Pauli exclusion principle, right? And so what that means is that no 2 electrons can occupy the exact same place. Duh. But the only way we can know that is by these things right up there. Those quantum numbers tell us where the electron is. So what that means is each electron is going to have a unique set of quantum numbers. Like in this shell, in this orbital, in that arrangement with that spin. Like that's only one electron gets to have that. Does that make sense? I hope so, because that's what we're talking about today, and maybe it will after a while. And this is really like just really complicated like way to find where the electron is. And the analogy everybody likes to use is this one. Like each seat in arena has its own unique thing, like section this, row this, seat that. You know what I mean? So section, row, and seat. It's not that difficult to find it in an arena because that's like a big solid thing. With like atoms and electrons, it's NL, M sub L, M sub S. It's just a little more like weird and abstract with electrons. Does that make sense? But really, again, that's really all that is like it tells us where the electrons are in there. So, oops, let me come up here. Let's just go through this again. The shell. This refers to like the energy level where the electrons are. The subshell, that's like, how would you describe that? That would be like all the electrons that are in the same like family orbital. Like there's a bunch of different orientations for the P. There's like 3 different ways the P can go, up and down, left and right, and then like right at you. So the subshell would be like all the electrons that are in that p orbital. Then the exact orbital tells us which one. Like, is it this s orbital? Is it, or I'm sorry, is it this p orbital, or that p orbital? Because remember, there's three p orbitals. Do you get what I'm saying? I don't know if any of this is really all that important, but look, let's talk about this. This is the energy for orbitals of a single electron atom. Hydrogen. This is why everything worked out so super well for hydrogen, but not so much for all the other stuff. And I want you to kind of see this for a minute. Here's 1s, here's 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, right? So these are all the orbitals and the energy level. And here's the thing: is if there's only one electron, right? We have an electron right. Where'd my pen go? Right here. Right. Let me get my pen going. Right. So we have one electron right here. That's all that's going on. Does it make sense? And usually we will denote this with an arrow going up. Like, in other words, spinning up, so the north is like facing up, is like one way to think about it. So what this means for this one single electron is that the energy only depends on the quantum number, like what energy level it's in, right? Because there's nothing else here to mess with this electron, like absolutely nothing. There. That's our equation. It's super duper easy. If we excite it up to the second energy level, it's just, n equals 2, then n equals 3, and then so on. So n equals 1, n equals 2, n equals 3, n equals 4. You guys get what I'm saying? But here's what actually happens in reality. So these are the energy of orbitals with multi-electron atoms. In other words, there's more than one. And so here's kind of what's going on down on that subatomic level. So if we put 2 electrons, we'll have one that's pointing up, and we'll have one that's pointing down. Because remember, you get 2 electrons per orbital. One that goes up, one goes down. When that happens, they kind of like get to attract to each other. 2s is here, right? Is on this level. But if you notice, there's a bit of an energy difference between 2s and 2p. Now, why is that? Well, if you remember shielding, this is kind of what's going on. It's the shielding, right? Because these things have to all sort of occupy the same space around the atom. They kind of get in each other's way. So you can think of it as 2s is here, and it kind of creates this little cloudiness of electrons, so that these guys here, right? So this electron and this electron and this electron, let's say this one had 3 electrons in the 2p orbital. If there are 3 electrons in there, these electrons have to see through this cloud, and then, oh wait, here, these electrons are making an electron cloud here, and they need to see through this electron cloud. So they're literally blocking that like proton pull, that like electronegativity, the pull that the nucleus has on the electrons. And because that attractive force is being blocked, this adds, it's like a little bit like further away. Does that make sense? So then this is next, and then 3s, and then 3p. But actually, before you can fill the 3d orbitals, you have to fill out the 4s orbitals, because it's all like, think of it as the shielding. The shielding just messes everything up. It gets messy, which is why this is like Bohr's model fell apart, right? It didn't quite take into account this like sort of shielding effect, and the fact that they're all going to be like sort of occupying the same place around this atom. But lo and behold, we have been able to figure it out. Okay, let me come like this so I can give me 1 second here. I'm going to try to erase this mess so that you guys can see a little bit better, or maybe not. Whatever, stupid computer. It's not. There you go. So the energy level, or the energy of the electron, it depends more on it's not just what energy level it's in. It's both energy level and the L number, which tells us which orbital. So it's the combination of energy level and orbital that tells us how much energy that electron actually has, because these two things sort of like blend together. I don't know if that makes sense, right? All right, let's just buzz through this. I don't really care. Yeah, we're interacting between both of them. Good for us. We're gonna go all the way through every single one. I don't know why I did that. So that gives us this thing called an Aufbau principle, right? Because this is all messy and it's crazy, but this principle right here, this is important for us to have like locked inside of our brain. This Aufbau principle basically says lowest energy first. They fill from bottom energy up to higher energy. Why? Because that just sort of makes sense, doesn't it? So in other words, what we're going to do is, or not what we're going to do, but what electrons do, is if you have a 1 electron atom, you get this. It's going to fill the lowest energy. Right? Now, that's hydrogen. Now, for helium, what's going to happen is we're not going to come here. Right? First, we're going to fill it like that, where they're all facing one direction, magnetically aligned. And then we're going to fill in opposite magnetic directions. So this energy level needs to get filled first. Now, when we add a 3rd electron, it'll go right here. 4th electron goes like that. A 5th electron. Now, here's where it's going to get messy. Or not messy, but like you'll see how it goes one at a time, and then they double. It's sort of like buses on a seat, right? Everybody sits one at a time until you have no choice, and then you double up. So 1, 2, 3, 4. If an electron, or I'm sorry, if an atom has 5, that's electron number 5, electron number 6, electron number 7, 8, 9, 10. Does that make sense? You get what I'm saying? So then you go to like 11 electrons, and then 12 electrons, right? And then 13, 14, 15, 16, 17, 18, right? So it fills lowest energy first, all like spins aligned, like, and that'll be 1 at a time, and then opposing spins to fit 2 electrons in each orbital. Got it? Clear as mud? Good. So what this means is that the most stable arrangement of electrons in subshell is one with the highest number of parallel spins. It's called Hund's rule. In other words, we try to get them all single as individual, only 1 electron per orbital as possible. As much as possible. It's not always possible, because what if this had 1 more electron? Well, then you'd have to have 1 more like that. But in doing so, we're like, hold on a second. Wait, where's my button? There's your button. All right. We're going to talk about, Hund's rule. We try to get them all like aligned 1 electron at a time. And also, the reason why they're all going to align like pointing in the same direction is because they just sort of do. Just go with me. It's like they all basically line up. Like if you take magnets and you throw them, they all tend to line up together. Nature. Let's just blame it on nature. There. So here's the thing. This is something that you should like just put inside your head, or make sure you have it in your book. But this is, it all follows in order. It's actually pretty simple to figure out the exact order that electrons fill all of the orbitals. And this is, you basically make this grid that kind of goes like this, right? What you do is you write down the orbitals for each energy level. And then I like to make it in a grid, like if I use lined notebook paper or something like this, I go like this. Oops. There. So the first energy level just has S. That's it. And N is 1, you have S. In N equals 2, you have S and you have P. In energy level 3, or N equals 3, you have S, P, D. In energy level 4, you have S, P, D, F. And then 5, there's S, P, D, F, G, but we're not going to get there. And then, so once you have that grid, you basically fill diagonal. So you start here, and you go diagonal like this, and then diagonal. You see how this is like going to be going? Oh, then I go here, then I'm going to go diagonal. You always go with diagonal. So that means first we're going to fill 1s. When the 1s is filled, we will fill the 2s. After the 2s is filled, we will follow 2p. Super easy, right? And then we're going to go to 3s. And now things will start to get weird. We're going to go, next is 3p, but now 4s gets filled before we fill 3d, then 4p, then 5s. Simple, right? And then after, but you just follow the flow. I'm following the flow. You just go diagonal. And that way you know the order in which the electrons will fill the orbitals. So it's kind of weird and complicated, but look, nature gave us a little trick, dare I say, a pattern to follow. Nature doing that. Who would have thought? And so what this tells us is that the energy level of the energy of the orbitals is not necessarily linear. It's a little messed up, but it still follows a pattern. It follows this pattern. It's not like straightforward, but what in nature is perfectly straight? Not much that I know. All right, so here, let's do this one. Write the 4 quantum numbers for an electron in a 3p orbital. Okay, so 4 quantum numbers for an electron, any electron, in a 3p. Okay, so the 4 quantum numbers are n, l, m sub l, and m sub s. Well, this right here, that's our n. So yeah, there's 3. So what does p stand for? What L number gives us p? Do you remember? I'll help you. It's 1. So the L is going to be 1. Yeah? So my M sub L, if you'll remember, it's a range. It can be -1, 0, or 1. So I'm going to go, let's go, I can have -1, I can have 0, and I can have +1. Yeah? I can also, and also the M sub S is it's either going to be a plus or a minus 1/2. So here's plus 1/2. Right? But see, I also need minus 1/2. So if I have my L's, I'm going to repeat my L values of -1, 0, and 1. What I'm going to do here is put minus 1/2. So these, L is 1, 1, 1, 1, 1, 3, 3, 3, 3, 3. Awesome. Does that make sense? So there are, what this is telling us is that there are 1, 2, 3, 4, 5, 6 possibilities, 6 quantum number combinations for an electron in a 3p orbital. I could write 3, 1, minus 1 plus 1/2. I could write 3, 1, 0 plus 1/2. Any one of those will be quantum numbers for an electron in a 3p orbital. Man, it's almost like if you just learn the pattern and follow the pattern, it'll like do that. Does that make sense? All right. So the electron configuration. This is basically a way to a way of notating where the electrons are, or like in which orbital all of our electrons are. And that is that sort of diagonal thing. If we start filling out that diagonal box diagram thing there, it'll give us the electron configuration, which is going to be a little more elevated than what you're used to seeing for Regents chemistry, right? So 1s1. That means there's one electron, right? One electron in an s orbital in energy level 1, or n equals 1. Does that make sense? So n is 1. S, that means L is 0, and there's 1, so we plus or minus 1/2. Does that make sense? All right. Why is this not going? There you go. So this is your electron configuration, and the diagram is that thing we do when I was like drawing up arrows and down arrows to show like electrons. So this is the orbital diagram for hydrogen. So in other words, there's one s, and this is that orbital. Like this is the 1s orbital, this little space. And now how many electrons is in there? 1. And I'm pointing it up. I could point it down, it doesn't really matter. There just has to be like just 1 electron in it. You dig? All right, so this is something that I want to talk to you guys about, because this is kind of like interesting. When we get into like electron configuration, this is where we learn about magnetism and how things become magnetic. Where am I going to put my face? How about I put my face right down here at the bottom? It doesn't. You guys don't pay attention to my face anyway. All right, so look, here are 2 different scenarios. In this scenario, this electron is spinning. Let's say it's spinning to the left, and this one is also spinning to the left. And if that's the case, we're going to say that it's up, right? So north is pointing up, right? Do you get what I'm saying? And so that means that this has a magnetic field where north is up here, and this has a magnetic field where north is up here. You got that? Now, if we put these two electrons together, like really close, like say in the same atom, these two magnetic fields can kind of like, they're like cumulative, right? You'll feel not just one magnetic force, but two magnetic forces, right? The magnetic force from two electrons. Now over here, same thing, only completely opposite. As we do this like electron configuration and we're filling them with electrons spinning up and electrons pointing down because of their spin, here we have an electron spinning to the left, and we said that that's north will point up, right? So if it's spinning to the left, north points up. If it spins to the right, north is going to point down. And so what this means is that this magnetic field that has a north up top and south on the bottom is going to be canceled by its counterpart over here, right? So that sort of north pull that we will experience out here is canceled out by the south pull that we feel out here. So if we put this thing next to a compass, nothing, because the north pulling it north is canceled by the south pulling it south. But this over here, this guy, with two electrons both pointing in the same direction, well, we put a compass on here. This little electron with its little magnetic force will pull the compass north, and this little electron with its magnetic field pulling north will pull the compass north. So this will have a magnetic field because all those little electrons align up and the magnetic fields become additive. They accumulate, and you can hold stuff on your fridge with these things. But this over here, if we have a substance that has all electrons up and down, no magnetic field happening there. Sorry. It's pretty interesting. Like, there are a lot of things that are magnetic that many people don't know about. Like oxygen is totally magnetic. You can totally do that with liquid oxygen. It's kind of amazing. You can actually, if you Google it, you can take specialized equipment to make liquefied oxygen. It's got to be really cool. But if you take two very strong magnets and put them very close together to create a magnetic field in between those two magnets, you can pour liquid oxygen into it and it'll be suspended in midair in between the two magnets, being held there by the magnetic field. It's totally magnetic. Who would have thought? But true. So paramagnetic means unpaired electrons. It means it's going to have an electric field. Here's an example. 2p. So p is the orbital, and there's like two electrons in it. Actually, that should be 2p2. Come on, man. Why am I putting over again? And then there's diamagnetic, which means the magnetic field died because all the electrons are paired and the magnetic fields cancel each other out, right? So 2p2, right? There's two electrons in the p orbitals. We're going to go 1, 2, put them all like alone and facing the right way, the same way first. And then this is 2p6. This is with the p orbital fully filled, because we would have gone first 1, then 2, then 3. All right, first all by themselves. Then we start doubling up 4, 5, 6. So this setup, this electron configuration, 0 magnetic field, no magnetic properties. This one going to have some magnetic properties. Dig? That's where that comes from. All right, let's check out this last one. Ooh, what is the maximum number of electrons that can be present in the principal level for which n equals 3? Boy. All right. For n equals 3, well, let's check it out. So for n equals 3, electrons can be present. L is going to be 0, 1, and 2, which means your m sub L, like the different orbitals you have, that's going to be 0, negative 1, 0, 0, and 1. This is like beyond frustrating when that happens, guys. I don't know who's happier, me or you, that this is the last of the last here. Whew. All right, so here we go. Sorry about the technical glitch. So we have the m sub L can be 0. The m sub L could be minus 1, it could be 0, it could be 1, and it could be minus 2. It could be minus 1, it could be 0, 1, and it can also be 2. So those are all my orbitals, right? So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. This tells me that there are 9 orbitals, right? So the next thing is going to be my m sub s. And this is going to be either plus 1/2 or minus 1/2. So there are 9 orbitals. Each holds 2 electrons, right? One is going to be plus, one's going to be minus. In other words, it'll be spinning up or down, right? So if there are 9 orbitals and each holds 2 electrons, you will have 18 electrons in all. Now let's go back and review how I did that, right? So the N tells us our energy level, and the L tells us which orbitals are in that energy level, and the orbital numbers are 0, 1, and 2. Those are the numbers in the equation, right? And so the m sub L, remember this corresponds to S, to a P, and to a D orbital, but these are the numbers in the equation. And so my m sub L's, in other words, like all these possibilities, if it's 0, it can only be 0. If L is 1, I get minus 1, 0, and 1. If my L is 2, it goes minus 2, 1, 0, 1, and 2. So these are all the orbitals, right? Right? And remember, each orbital holds 2, so it has to be 18 electrons in all. I hope that works for you. All right, this is getting messy here, guys. All right, give me a second. Let me get this back to the... Oh, boy. All right, let's see if we can answer this problem. An oxygen has a total of 8 electrons. Write the 4 quantum numbers for each electron in the ground state. Let's do a grid. Anytime we're listing all of them, let's just do a grid. So 4 quantum numbers are N, L, M sub L, and M sub S. Okay, so let's start the first energy level. N equals 1. The L will always be 0, and then M sub L is just 0. And then my M sub S is plus 1/2. And then we have the same thing, only with negative. So remember, so this is like what happens for the guy with like the opposite spin. Okay, so now let's go to energy level 2. So for energy level 2, we'll have an L is 0. And if we have an L is 0, that means that the M is 0, and we'll have a plus 1/2. Same exact thing with a negative 1/2 also, right? So we have to have the same everything. Right? So this is the one with the upspin, that's like the one with the downspin. So for energy level 2, our L option, so if N equals 2, if N equals 1, L equals 0. If N equals 2, L equals 0, and L can equal 1. Remember, so you have 2 options. So let's go to the L equals 1. So in my energy level 2, I have an L is equal to 1. So if that's the case, if L equals 1, my M sub L's is equal to negative 1, 0, and 1. So I have negative 1, 0, and 1 if my L is equal to 1. See if this works today. Right, we're still in energy level 2. We're still in energy level 2. So these are the 3 options for my L equals 1. And I'm going to make these all plus 1/2. Right, so that there is for L equals 1. And all plus 1/2. So now I got to fill the others, like with the minus 1/2. So it'll be exactly like this, but I'm going to populate it with minus 1/2. But I only need one more, right? Because this is 1 electron, 2 electrons, 3rd, 4th, 5th, 6th, 7th, And so my eighth electron will be 2, 1. Let's just start with -1. And I'm going to make it, instead of +1/2, I'll make it -1/2. There. It can be anything. But see, if I made these negatives, it's fine as long as this one would be positive. They're just like opposite spin. Picking up what I'm putting down? It's good, clean, wholesome fun right there, guys. Electron configuration. All right. Also, not for nothing, but check this out, man. Table 7.3 has all these things that we call electron configuration for all of the elements in shorthand. So it doesn't like take up pages and pages. So here, I'm going to help you read this, right? So here it ends with helium, 1s2, and that means that the first energy level is full. So when we move to the next energy level, right, energy levels 2, for lithium, it is basically a 1s interior, and on the outside, the valence electron is a 2s1 electron. For beryllium, it's a 2s2. For boron, it's 2s2, 2p1. In other words, there are, in energy level 2, there are 2 electrons in the s and 1 electron in the p. You guys get what I'm saying? There it is. It all follows, and not all of them follow exactly, but it's all listed there for your perusal and looking up knowledge. And here, my friends, is why the periodic table looks exactly the way it does. Because these two, group 1 and 2, these are all very, very similar in chemical and physical properties, because these valence electrons are all in the s shell. That's why they all act like s shell elements. This block, these are where you get your p shells being filled. That's why they're all sort of blocked together and like really trippy and weird and all over the place. And these are where the d orbitals are being filled. That's why they all kind of act vaguely similar. They're all mostly like silvery looking metals. And here is where the f shells are being filled. These guys all behave. These two groups behave so similar that it took until the 1940s before we could actually distinguish between them. They behaved so similar. And so that's basically why the periodic table looks the way it does. You guys get what I'm saying? But here's a little fun thing. As you go across, energy level 1, energy level 2, energy level 3. But remember, because of the shielding, things get a little like cattywampusy with their energy levels. Well, at the 4th energy level, right, when you start adding into the d orbitals, which is in regions where we're like, we're not even touching the chemistry of them, because dude, their valence electrons are in like deep inside, they're on the 3rd energy level. You know what I mean? So you go 4s, then when you go to the your transition metals here, the principal energy level that you're filling is 1 energy level lower than this side or this side. Do you get it? So it's like 4s, then your 3ds, then your 4ps. Then 5s, 4d, 5p. 6s, 5d, 6p. There's a little bit of a pattern there. It'll be really nice if you have to, like, say, figure out electron configurations and stuff. Who would do that? Me. To you. I like this. Write the ground state electron configuration for sulfur. All right, so here's sulfur. First thing I'm doing, looking up the atomic number of sulfur. Oh, 16. So I got to come up with 16 electrons. Okay. So I'm going to go back to that grid thing, right? Where I have 1s, then 2s, 2p, 3s, 3, spd, 3d, 4s, 4p, 4d, spd, 4f. And they fill diagonally. So remember, 2 electrons in each one. So there's 1. So 1s2, because I'll fill this one going like this. Then I come here, 2s, right? Because s can only have 2. Then I'm going to go 2p. Now p, there are 3 orbitals, and you can fill this all the way up to 6. But let's do a quick electron count. 1, 2, 3, 4, 6. That makes me 10. Next is 3s. 3s2. Then I'm going to go to 3p. So 2 electrons. If I get to here, I'm at 4. Here I'm at 10. Here I'm at 12. And I only need to get to, what did I say, 16? So sp4, because this is going to hold all the way up to 6. How can you tell? 1, 2, 3, 4, 5, 6. Okay. You dig? Bam. Done. Easy. This one, palladium, which is diamagnetic. I'm not doing this to you guys. Won't do it. Not going to do it. This is like, it goes against this rule. And the reason it goes against this rule is because it shifts things so that all the electrons are paired up like this, and it's diamagnetic. It kills the magnetic field. Why does it do that? It's a little more stable that way. That's why. But I'm not gonna make you guys do anything like that. What I am gonna make you do is outline 7, 8, and 7, 9, and then this stuff is gonna be for tomorrow, like the next day after this. Your last homework assignment. Yeah, because then we're gonna get ready for the final exam. After we review and have a vocab quiz and then an exam and then a final exam, and oh. Woo! Hold on tight, guys. We're almost there.